Section 4.6, limits at infinity and asymptotes. We've used first and second derivatives to describe the shape of a graph, talking about maximums and minimums, intervals of increasing, decreasing, as well as where the graph crosses the x-axis. Now we're going to use the limits as x goes to positive or negative infinity to tell us what happens to our function at the ends. We call this the end behavior. So first let's take a look at the function 2 plus 1 over x. If we were to let x go to positive infinity, then we're talking about plugging in very large numbers for x. And if we were walking along the number line, we're taking the x goes to positive infinity to the extreme. Now in this picture you only see x going up to positive 8 and a little beyond, but you can kind of picture what would happen if x went even larger. It looks like our curve is coming close to the line y equals 2. It's like hugging up to that curve, but it's not actually going to touch it. It just comes up side by side real close. So just from looking at the picture, we can conclude that the limit as x goes to positive infinity of 2 plus 1 over x is equal to 2. And we can actually argue this algebraically as well. We know that the limit of a constant, like 2, is just equal to 2. So the first term, 2, that one's pretty straightforward. It's the second term that requires a little bit of thinking. 1 over x, let's think about that. You could create a table of values to see what happens here, but essentially you're taking the number 1 and you're dividing it by a number that's getting larger and larger. Each time you compute 1 divided by x with a larger number for x, this number, 1 over x, gets smaller and smaller. So as x gets big, 1 over x gets so small that we might as well call it 0. The same thing happens when we look at x going to negative infinity. So if we've walked on the number line all the way to the left, we can see that our function looks like it's again approaching the line y equals 2, getting really, really close to it, hugging up against it, but not ever crossing it. And from that, we know that the limit as x goes to negative infinity for our function 2 plus 1 over x, it's also approaching 2. And we can use the same argument here that 1 divided by x, as x is getting larger and larger towards, not larger and larger, what would I mean to say? Gets smaller and smaller. This value, 1 divided by x, is equal to 0. We can also check this using a table of values. So as x goes to positive infinity, we can pick different values for x, like 10, 100, 1,000, or 10,000. We'll plug each one of these numbers into our function, and we can see that as our number gets larger and larger, the function value gets closer and closer to 2. And the same thing goes for x approaching negative infinity. Instead of picking positive 10, 100, 1,000, 10,000, we'll pick negative 10, negative 100, negative 1,000, negative 10,000. And here we can see that our function value, again, is approaching 2. So that leads us to a definition for a limit, or an infinite limit, limit at infinity. So when we talk about finding a limit at infinity, we're saying let the independent variable become sufficiently large, like the idea infinity. And if the function lands on a particular value or starts to approach a particular value, then we say that the function f has a limit at infinity equal to L. And we can say the same thing for x going towards negative infinity. Now, the next definition on the page is for a horizontal asymptote. We have seen asymptotes in math class before, and typically we have seen vertical asymptotes. So let me remind you that if we have an xy plane, maybe we have a graph that looks like this. There's a vertical asymptote right on the y-axis. This graph will never cross the vertical asymptote, and that has to do with the definition of a one-to-one function. Our functions are still one-to-one, but they can actually cross over their horizontal asymptote more than once. So we have three different pictures down here. First picture, the function is approaching the horizontal asymptote from the top. Second picture, function is approaching the horizontal asymptote from the bottom. So you could have either of these two cases. Or you can have a horizontal asymptote where your function wiggles above and below and eventually settles down onto the asymptote as x gets very, very large. Now, in the definition that we have, the horizontal asymptote is defined to be the limit value when x gets sufficiently large. So if x is going to positive infinity and the function has a limit that's approaching L, then we would say that there's a horizontal asymptote at the line y equals L. Or we could have x approaching negative infinity and the function limiting value is approaching L, then we could say that that is also a horizontal asymptote. Now, it is possible for the limit as x goes to positive infinity to equal one value, and the limit for x to go to negative infinity to equal a different value. So it is possible for one function to have more than one horizontal asymptote. Let's practice computing some of these things. So for the function 5 minus 2 over x squared, we're going to evaluate each of the limits where x is approaching positive infinity or x is approaching negative infinity. So let's go ahead and plug our functions in. Remember, we said that the limit of a constant is always equal to that constant, so we can quickly just copy the 5 over. It's the 2 over x squared term that requires some attention. If we're dividing by x squared and x is getting sufficiently large, then 2 divided by a really, really big number, it's going to end up being a 0, just like it was in the case for 1 over x. In fact, any term that has x in the denominator with a constant on top, that's going to end up going to 0. So in each case, our function is approaching the limiting value 5. And now that we've calculated each of these limits towards infinity, we can see that our function is going to have a horizontal asymptote at the line y equals 5. And I have a little picture of our function here. The function's plotted in blue, the horizontal asymptote is plotted in orange, and we can see that as x gets very, very large, our function comes up very close to the line y equals 5. Same thing for when x gets very, very small. Looking at our next function, we have sine x over x, and here we'd like to again evaluate the limit as x goes to positive infinity, as well as the limit x goes to negative infinity for the function sine x over x. Now we've seen this function before, but I want you to know the difference. Before, when we talked about this function, x was not approaching infinity, x was approaching 0. And we said that the Squeeze Theorem showed us this limit is approaching 1, which we can definitely confirm that on our graph. Around x equals 0, our function is approaching 1. But that is not what this problem is asking us. So it's good if we remember that, but make sure that you don't confuse that with what this problem is asking. This problem is saying let x go to infinity, not 0. So in that case, if you tried to plug in infinity over infinity, we don't really know how to deal with that, so let's not go there. I did say that anytime you have x in the denominator and a constant on top, that the quotient would go to 0, but we don't have a constant on top, we have sine x on top. So to be able to evaluate these limits, we have to really think critically about our function. So what do we know about sine? Well, we do know that the sine function itself is an oscillatory function that oscillates between two numbers. The largest value up here at our top is 1. The smallest value down here at our bottom is -1. So we know that sine x is always less than or equal to +1, always greater than or equal to -1. But that's not the function we're working with. We're working with sine x over x. So to make this inequality match, we'll divide each term by x. And now we can see that sine x over x is always between -1 over x and +1 over x. And if we take the limit of each term in this inequality, let's do the limit as x goes to infinity first. We can use the Squeeze Theorem here to see that the limit as x goes to infinity is squeezed between these two outside functions, -1 over x and +1 over x. Well, now we do have x in the denominator with a constant on top, so as x gets infinitely large, the limit of -1 over x goes to 0. And for +1 over x, we have the same argument, which means by the Squeeze Theorem, the limit of what is in between those two things also has to be equal to 0. So we can argue that the limit as x goes to infinity of sine x over x is equal to 0. And we can actually use the same argument for -infinity by saying, by just throwing in the fact that x is going to -infinity, we'd still get 0. So this tells us that we have a horizontal asymptote that is right on the x-axis, and we can see that in our graph that our function is wiggling around the x-axis, but as we continue further and further out, it would get flatter and flatter until it eventually was hugged up right against the x-axis. Now let's take a look at another function, tangent inverse of x. Now, we've seen tangent inverse in a trig class, I'm sure, but we're going to actually go back to tangent x to help us on this one. So first, let's set up our limits. X is going to +infinity, x is going to -infinity, and we're looking at tangent inverse of x. If we think back to the graph of tangent x, we can remember that there are two vertical asymptotes. One that occurs at +π/2, one that occurs at -π/2. This means that as x approaches +π/2, our function goes up to infinity. In other words, tangent at π/2 is pretty much equal to infinity. And if we wanted to do the inverse, that's where you get to swap x and y, so tangent x is equal to y, the inverse would say tangent inverse of y is equal to x. Well, if we swapped x at π/2 with y at infinity, that would look like tangent inverse of infinity is equal to π/2. So it's basically just swapping those around. So as x gets very, very large, tangent inverse approaches +π/2. And as x gets very, very small, tangent inverse would approach the other asymptote at -π/2. In this case, we have two horizontal asymptotes, one that occurs at, and we can see that in the picture at the top right of the screen, one that occurs at y equals +π/2, the other that occurs at y equals -π/2. Next, we're going to talk about computing limits at infinity for functions that don't really have a horizontal asymptote. So if we wanted to do this whole process for a function like x cubed, and we said, okay, let's let x go to infinity. What happens to x cubed? Well, just looking at the graph, we can see that this function continues on without bound, up and up and up, all the way to infinity. So we could say that as x goes to positive infinity, x cubed goes to positive infinity. And if we were to let x get smaller and smaller, we could see that our function continues in the direction of negative infinity without bound. So in that case, we could say that the limit as x goes to negative infinity of x cubed, that's going to be equal to negative infinity. So we have an informal definition here. We say that a function has an infinite limit at infinity when the limit as x goes to infinity allows the function to approach infinity. So f is becoming arbitrarily large for a sufficiently large x. And we can make the same argument for if the function were approaching negative infinity, and we can make the same argument for when x is going to negative infinity, our function could approach positive or negative infinity. These ideas, these limits where x goes to positive or negative infinity, they help us identify the end behavior of a function, because x getting crazy large is what takes us all the way to the left and all the way to the right of our graph. So we call that the end behavior. And there's only 3 different scenarios we could have. Our function could have a horizontal asymptote, or maybe multiple horizontal asymptotes like we saw in the tangent inverse function. The function can blow up to positive or negative infinity, or the function does neither. In this case, it might be some oscillatory function like sine or cosine. Let's specifically look at polynomial functions. So these are the ones that are just powers of x. So you'll see like an times x to the n plus an minus 1, x to the n minus 1, plus as many terms as you need until you get down to a sub 1 times x plus a sub 0. So this is our polynomial function. And there's a few basic graphs that we need to have burned into our brain. For example, x to the power of 1, that's just a line. X to the power of 2, that's a quadratic. X to the power of 3, that's a cubic. X to the power of 4, we just say that's x to the power of 4. We don't give that a fancy name. Or x to the power of 5. Now, something that's pretty neat about polynomial functions is that at the very most, each one of these graphs will cross the x-axis the same number of times as the value of the exponent. So x to the first can only cross the x-axis once. X squared could possibly cross the x-axis twice. X cubed might hit it 3 times. X to the 4th could hit it a maximum of 4 times, and x to the 5th could hit it a maximum of 5 times. So that's how you can help remember how to draw each of these functions. Now, we're not really talking about x-intercepts here. We want to talk about the end behavior. But I want to point out something that's happening. X to the first power, that's an odd exponent. X squared, that's even exponent. X cubed is another odd one, x to the 4th is even, and x to the 5th is odd as well. Notice that with the 2 even graphs, the end behavior was identical on the left side and the right side. So as x goes to plus or minus infinity, the end points both went up, so the end behavior matched. However, with the odd functions, the end behavior was opposite. And what I mean by that is that maybe as x went to positive infinity, our function was going up to positive infinity. But as x went to negative infinity, our function went down to negative infinity, which is different than what happens in an even graph. In an even graph, both endpoints point up. In an odd graph, one points up, one points down. So this is a cool shortcut whenever you're looking for the end behavior of a polynomial. Let's do an example of one. So negative 5x cubed. We'll do the limit as x goes to positive infinity, and the limit as x goes to negative infinity. Whoa. Now we know that the x cubed function looks kind of like this, but if we threw a negative on that, this would flip over, so our graph would actually look like this. Which means we know that the limit as x goes to positive infinity is going to go down to negative infinity. And the limit as x goes to negative infinity, the function is going to go up to positive infinity. Oops, I forgot my negative on that first limit. There we go. Let's write it again. And this agrees with what we just talked about. The function had an odd exponent. The degree was odd, which means that the end behavior should be opposite. What about for a function like 2 times x to the 4th power? Well, we can use our shortcut here to say whatever the limit is when x goes to positive infinity, it should be equal to the limit when x goes to negative infinity. Well, if we think about x to the 4th, the bigger number we plug in, the bigger it gets. So this is going to blow up to positive infinity, and that should match the limit when x goes to negative infinity, basically because x raised to the 4th power consumes the negative. It goes away, right? Anytime you have an even exponent, the negative number is gone. So both of these approach positive infinity. Let's take a look at an algebraic function, so a rational function. Rather than looking at those polynomials, let's look at something a little more complicated. To find these limits, we're going to use a little bit of a trick. Because we know that the limit where x goes to infinity of a constant over x to some power gives us 0, we're going to force that to happen in our function. To force that to happen, we're going to look in the denominator. In this case, that's 2x plus 5, and we're going to pick the largest power of x. Which is x to the 1st power, right? If we're looking at 2x plus 5, the largest power of x is x to the 1st power. So we'll divide every term in our function by x to the 1st power. So instead of 3x minus 1 in our numerator, we'll have 3x divided by x minus 1 over x. And then instead of 2x plus 5 in our denominator, we'll have 2x divided by 5, and then 5 divided by x. Now some of those terms are going to reduce. There's x's in the numerators and the denominators. So 3x divided by x, those x's divide off, like they're gone. And then 2x over x, those x's divide off, like they're gone. So we really have 3 minus 1 over x, and the denominator would be 2 plus 5 over. The 3 and the 2, those are constants, So it doesn't matter what x is doing, they're going to stay where they are. The 1 over x would go to 0, the 5 over x would go to 0. So for this function, as x gets infinitely large, the function approaches 3/2. We can do the same argument for when x goes to negative infinity. Again, using the function that happens after we divide by the largest power of x, we'll look at 3 minus 1 over x, 2 plus 5 over x. As x goes to negative infinity, 3 over 2 doesn't change. And even though x is going to negative infinity, this negative 1 over x still goes to 0, and this 5 over x also goes to 0. So we can see that we have a horizontal asymptote at the line y equals 3/2. Let's look at another algebraic function. We'll use the same process. So looking at our denominator, the largest power of x is x cubed. So let's do our scratch work first. Let's divide every term by x cubed. And looking through, we can see that the 3x squared over x cubed, that's going to simplify to be 3 over x. The 2x over x cubed is going to simplify to be 2 over x squared. The 4x cubed over x cubed simplifies to 4. Then we have minus 5 over x squared plus 7 over x cubed. And when we apply our limit, where x goes to infinity, to that version of the function, we have plenty of terms that zero out. So every term in the numerator goes to 0, and our denominator, we end up with 4 minus 0 plus 0. So it's essentially 0 divided by 4, which is equal to 0. And the exact same thing would happen if we went to negative infinity, because we have a bunch of terms going to 0. I should write that in there, huh? 3 over x plus 2 over x squared, 4 minus 5 over x squared plus 7 over x cubed. This also goes to 0. So then we would say that we have a horizontal asymptote at y equals 0. Let's take a look at another function here, this time 3x plus 4x. I think that's a typo. Let me double check. And it was. I meant for that to be 3x squared plus 4x over x plus 2. So we're going to repeat this process, find the largest term in the denominator, that's just x, divide that on every term in our function. And again, this is literally just to make our calculation easier when computing the limit. We like to have terms that have x in the denominator because as x gets crazy large, those terms go to 0. So we end up with 3x plus 4 in the numerator and 1 plus 2 over x in the denominator. As x goes to positive infinity, for that version of our function, 3x plus 4 over 1 plus 2 over x. We can see that the term 2 over x goes to 0, but also notice that this 3 times x in the numerator, as x gets really, really large, that term gets so big that it takes over everything else. So this function is actually going to go off to positive infinity. And when we look at x approaching negative infinity, we would make a similar argument, 3x plus 4 over 1 plus 2 divided by x. That 2 divided by x goes to 0, but the 3 times x, when x gets super small, very, very negative, that's going to go to negative infinity. So in this case, we don't have an asymptote. In fact, we have our function going up, blowing up to positive infinity, and blowing up to negative infinity. We just looked at 3 separate cases of end behavior for algebraic rational functions. The first one we looked at, the degree of the numerator matched the degree of the denominator. In that case, our function had a horizontal asymptote that was equal to the coefficients from the numerator and the denominator on the highest degree term. So if we're a little rusty on what it means to be a rational function, remember that a rational function has a polynomial on top, polynomial on bottom, and the leading coefficient for each one of those polynomials is denoted by a sub n and b sub m. So our limit, as x went to positive and negative infinity, gave us the horizontal asymptote equal to the ratio of those leading coefficients. In the second case, we saw a numerator that had a degree smaller than the denominator. And in this case, the horizontal asymptote was on the x-axis, the y equals 0 line. And then in our last case, we had the degree of the numerator greater than the degree of the denominator. And in that case, we had an asymptote that blew up to positive infinity or negative infinity. So when we have a rational function where the numerator's degree is larger than the denominator, we could use long division to reduce the degree of the numerator, separating it into a kind of like a mixed number, but for polynomials. And in that case, we can see that the remainder over the quotient has a 0 limit, and that g of x function, when we subtract it from our original function, is going to give us a 0 as x goes to positive or negative infinity. In this special case, where the degree difference, so the degree in the numerator is just 1 more than the degree of the denominator, the function is going to have a g of x when you do your long division that is linear, and a linear function is going to result in an oblique asymptote. If you want to know more about this, I'd encourage you to read the text. We're not going to do much more in terms of an oblique asymptote, but I just wanted to cover the 3 scenarios for rational functions. You either have larger degree on top, smaller degree on bottom. That will give you a horizontal asymptote that can be found by looking at the leading coefficient of the numerator and the denominator. Or you could have the degree on the numerator smaller than the denominator. That will give you a horizontal asymptote at the x-axis. Or you can have the degree of the numerator big, the degree of the denominator small. In that case, you don't have a horizontal asymptote, but you could possibly have an oblique asymptote.